All right, got two sort of announcements, okay? Number one, I did get on Blackboard. Well, first I got your syllabus updated. I got all the corrections made that I remembered that we talked about and I found. Got it updated and put on Blackboard under content. I just had a little something to do on the research paper instructions. I got that done. I put those in Blackboard under content. I got my locator card done. I finally figured out what hours I'll be working, what my office hours will be, when I'll be in and out, that kind of stuff. So that's now on Blackboard under content. And I did find a few websites or YouTube videos or other things that either students had given me or that I found myself that I thought might be helpful for this course. I put those under content. I also got the first two classes. I had uploaded those to YouTube, but once in YouTube, I put them in a playlist, and they're now in the playlist. And I got that playlist address link and put it in Blackboard too, under content. So what you look for there is MTH238 YouTube videos. That's ours. When you click on that, you're going to see a huge number of videos, way more than we've done. What I did, I put that in the same file that I did last term's on. So you'll have everything out there. Won't be in the same thing. In fact, the ones at the beginning are from last term, and only the last two at the very bottom, I think there's 30 or something like that out there, go to the very bottom, and those two are the ones that we've done so far. Today will be third, and I may take out one at the top, because if it's something I've done both last term and this term, I want you to look at this term's. Okay. So there may be a little bit of overlap, but the older ones are at the top, the newer ones at the bottom. Okay, so all that's there, and I think Blackboard's ready to go. It just will take my loading the new classes onto YouTube, then putting them into the playlist, and they'll automatically be linked. And I may take out some of the older ones while I'm doing that. Now, the one other announcement, and this is it really doesn't impact this class a lot unless you happen to be here on Tuesday and Thursday as well. I don't know if you are or not. Well, I'll put it out there for the others. On tomorrow, I have a doctor's appointment. My hematologist only sees patients on Tuesday mornings. Tomorrow's is scheduled, I think, for 11:20, which means I have to leave campus by 10:20. Well, no, I have to be at the lab by 10:20 to get the blood work done, and that means I have to leave campus shortly after my 9:15 class is over. My 8 to 9:15 class is over. So basically, I'm missing my 9:30 class completely. So normally I have office hours on Tuesdays from 10:45 until 12:30. Since my doctor's appointment is smack in the middle of that, I won't be in my office probably any of those office hours. I may not even be back by 12:30, but my 12:30 class knows not to go anywhere, that I will be here. I may be a little late. Or if I get here a little before 12:30, basically not going to have time for many office hours anyway. Okay, so tomorrow, basically no office hours. On Thursday, I'll be making up the class that we missed tomorrow. Okay, so that means at 10:45, when I normally go to the office, I'll just be starting the second part of the class, and I'll go 10:45 until 12. So my office hours on Thursday are only going to be 12 to 12:30. Okay, so basically no office hours tomorrow because I've got a doctor's appointment, and Thursday limited office hours only 12 to 12:30 rather than 10:45 to 12:30 because I'll be making up the class that I missed tomorrow. Okay, so those two things. And the other thing I was saying earlier was I got the syllabus updated, the research paper instructions updated, my locator card done, and I got all those on Blackboard under content. I also put a few either websites or YouTube videos or things that either I found or students have passed along to me that they liked. I put those on the blackboard too, under content, in case you find those helpful for this class. And I also did the link to the playlist, and that's under content as well. That's Math 238 YouTube videos. If you click on that, you'll get the playlist. Now that playlist contains something like 30 or 30 some odd videos. The first bunches of those are from last term. Only the last two at the bottom are from this term. But I left those up there in case you wanted to either see what we did last time or see if I did it any differently. But I'll be taking off when we do one, like the one I did for syllabus last term I've already taken off. And the one that on 1.1, I probably left that up there when we finish 1.1. I'll take off last fall's 1.1 and leave on this fall. The new ones are at the bottom, the older ones are at the top. So to see what we did this term, scroll to the bottom. All right, any questions? Okay, all right, we'll wait. We won't wait for them. And by the way, I didn't mark you. I saw you come in, but I forgot to mark you. And hopefully Nigel will be here. I don't know if we still have Charles Lee Jennings or not. He never has shown, and he originally was indicated not paid. If he wasn't paid, he got removed. Now, something you had asked before, when I tried to mark you, I can't remember now what the deal was. They already had NE down for you, not enrolled in the class, so I couldn't put anything there. And then I don't know if the payment went over or not. And the one time I looked at it, I don't think you were. I can't remember if you weren't listed or something. So I couldn't do anything until Friday. And when I did it Friday, I don't know if that was too late for the.
It'll come next.
It'll come, yeah. Okay. Yeah. So I knew that had been a concern, but I couldn't do anything about it. I tried, but I couldn't. All right, we are now recording, so let's get the slideshow set up from current slide. Any questions on anything we've done up till now? All right, what we're doing last time, we're in section 1.1, chapter 1, definition terminology, and one of these things is how do you verify a solution? And that's what we were doing. We did example 3.3a. Let's do 3b. Here is 3b. Let me get my pen activated. Okay. I hope it is. No, it's not. There. I think I got it this time. Yes, I did. Took a while. All right. Here is, oops. Thought I turned on the projector. I guess I didn't. There it is. Okay. Example 3b in section 1.1, page 5. Y double prime minus 2y prime plus y is equal to 0. Okay? Now, that's our differential equation. Can someone tell me some features, characteristics of that differential equation? What kind is it? Any of you tell? Either of you tell? Yeah, remember there's different ways to class a differential equation. There's classification by type, order, and linearity. What's the type? Ordinary differential equation. Perfect. What's the order? First order. None of your y or y primes or any of the y primes are squared or raised to higher powers. So that's a first order, ordinary differential equation. And what's the linearity? It's linear. It would be nonlinear. Let's see. No, wait. It's not what we're. Yeah, linearity. I think I said that wrong. It's first order in that that your derivatives, no, I'm sorry. The order is what? It's not first order. Second order, because it's y double prime. It's the order of the maximum differentiation. That's y double prime, the second derivative of y. So it's the second order linear, okay? All of those are to the first power, so therefore the y is to the first power. You don't have any cross. You don't have a y prime and a y in the same term. You don't have a y squared or a y prime squared. Now, one other thing, and we haven't gotten there yet, but I'll just tell you now, that's also what we call a homogeneous equation because it's equal to 0. If that had been equal to x or 3 to the x or 7 or something else which is not, has some function of x or constant or something else, that would not be homogeneous. With a 0 there, it is homogeneous. Okay. Yeah. If none of these are raised to a power, you have cross terms. Like if you had a y double prime, y prime minus 2y prime, that would not be linear because you have 2 of the y's multiplied by each other. Or if you had y double prime minus 2y prime squared, that would not be linear. Or y cubed, or y to the 1/2 power or something, that would not be linear. Each of these y terms, and the derivatives of y term, are to the first power only. So that's the linearity part. The fact that the order, this is the maximum derivative there, is the second derivative, so it's the second order. Okay. Second order, yeah. I know someone said that, and I agreed before. I was thinking linearity, but not order. Okay. Now, that wasn't what this problem was asking for. That was review, okay? What it's asking for is to verify that y is equal to x e to the x is a solution for that linear, ordinary, second order differential equation, okay? So what would you have to do before you can verify that? Yes, good for answer. Y prime is equal to what? To do that, you got to use a what rule? Product rule. And what does the product rule tell you? A little louder? Okay. You can say it either way you want to. I like it this way. The first factor times the derivative of the second plus the derivative of the first times the second for this problem. You can do that first if you want to. It doesn't matter which order you do, just you got to do both of them. Okay, if you do the derivative of the first times the second, that would be e to the x plus, is that what you said? I couldn't hear. Okay, plus x e to the x. Okay, now most of the time I like to put the bigger term first, but it doesn't really matter. What else have we got to do? You got to do a second derivative, y double prime, because this is second order ordinary differential equation. Especially with that first term, all you do is take its derivative. What is it? E to the x. And the second term, when you take its derivative, it's just like the y was before, so it's just going to be a repeat of what you had before, right? Derivative of this is that. Derivative of this is that. Both of those terms. So say, yeah, that would then be e to the x plus x e to the x, right? Which would then be 2e to the x plus x e to the x. Everybody see that? Okay? Now we can go back and plug and chug. Our original differential equation said y double prime, which we found to be 2e to the x plus x e to the x minus 2 times our y prime, which was e to the x plus x e to the x, plus our y, which was x e to the x, this is suggesting that that's equal to 0. Let's see if it is. This would be 2e to the x plus xe to the x minus 2e to the x minus 2xe to the x plus x, can't write, e to the x. Is that equal to 0? Well, let's see. Here we have a 2e to the x. Here we have a minus 2e to the x. They add to 0. Here we have a positive e to the x plus another e to the x. That's 2e to the x, 2xe to the x minus 2xe to the x. That sure enough adds to 0. 0 is equal to 0. Yes, that was a solution. Now, just because it's a solution doesn't mean it's the solution. There may be other solutions as well. We'll get there later. This is how you verify that something is a solution. Plug it in. But not just it, plug in its various derivatives that are called for.
Did you plug 2 e to the x plus x dx into the y's?
What I did, we found out, they gave us that, right? We found out this one, right? And we found out this one. Right. Okay, so what we did, the y double prime, which we found to be that, we wrote it down, right?
Right.
Minus 2 times y prime, which we found to be that. So we wrote that in there. Right?
Okay, now I see what you did.
Yeah. Plus y, which was what they gave us. We put that in. And then we started clearing parentheses, combining like terms, and sure enough, it turned out 0. 0 is equal to 0. So that is not necessarily your total solution, your final solution. It just verified that is a solution to that ordinary differential equation. Second order ordinary differential equation. Okay? See how it works? All right. Now, for instance, that's not the only, as I was alluding to, the only solution. I'll give you another solution. I'll just do it right off the top of my head. Of course, I'll look in the book too, but I know it works. Y is equal to 0. Will that work? Y prime would then be 0. Y double prime would be 0. Is 0 minus 2 times 0 plus 0 equals 0? Yes, it is. So, sure enough, that's not the only solution. There's another one. Y is equal to 0 is a solution. Okay? In fact, you can have, I know, at least up to 2, because this is a second order, but they may have an infinite number of solutions. Okay? This being 1, y is equal to 0 being 1. Can't guarantee you for this one there will be others, but I have a sneaking suspicion there will be. Okay? And we'll learn those later. But right now we're just getting used to differential equations, what it means. Okay. Now, you have an e-book, is that right? Do you have any book? Okay. Okay. As you, and when you do, you'll see that a function versus a solution. Here is a function y is equal to 1 over x. Okay? It has a lobe down here and a lobe up here. 1 over 1, 1 over 2, 1 over 3, or 1 over 1/2, 1 over 3, or 1/3. That's the solution. But also you have the one down here for negative x. Negative 1 would be negative 1. Negative 2 would be negative 1/2. Negative 1/2 would be a negative 2. So you have 2 lobes. However, if you had a solution, y is equal to 1 over x, that can't be your solution for all things, for only some interval. The interval could not be from negative 1 to 1 because that's not even defined at 0. So that could be a solution from 1 to infinity. It could be a solution from 1/2 half to 3 halves, or anything like that, or it could be a solution from -2 to -1. You could, the deal is you can't include 0 in there. So that could be a solution over just a limited part of your domain. Maybe a pretty large part, but still not the entire domain. Now, there is also, and this is flicking back to Cal 1 or Cal 2, explicit and implicit solutions, okay? A solution in which the dependent variable is expressed solely in terms of the independent variable, that's said to be an explicit solution. Like that. Y is equal to x e to the x. The y is a function of x alone. Okay? And it may have more terms there, more variables, more independent variable, more constants, whatever. Okay. Now, what if you had a equation that you could not deal with unless you, that would be an example of an explicit solution. You can express y as a function of x. Okay. An implicit solution of an ordinary differential equation, here's the what they give on that. Okay. A relation g of x and y equals 0. Now notice they didn't actually call it a function, they call it a relation. It's said to be an implicit solution, I abbreviate like crazy, of an ordinary differential equation, ODE, ordinary differential equation, such as you have in equation 4. Okay, goes back a couple of pages, and that would be something like some function of x's, y's, y primes, y double primes, dot, 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 up to y to the nth. That's the nth derivative of y. That function equal to 0. If you moved everything to one side and did that. Okay? Now this is a relation g of xy can be an ordinary, it's said to be an implicit solution of the ordinary differential equation, this one, f, on an interval I, okay, on the interval I, provided there exists at least one function phi, now that's not 0, that's the function phi, that satisfies the relation as well as the differential equation on I. And here's my, okay, we got our 3 regulars here. Don't know if we're going to have Charles Lee Jennings or not. Charles, if you're listening to me, we need some sort of verification you're there. So call me, send me your page on your syllabus that you've read it and understand it. Email that to me. Send me your paper topic. Send me your paper. Any of that would show you're in the class, and then I can start marking you on the roll if they have you on the roll. They did remove all unpaid students. I don't know if you were paid or not, so check it out. See. Okay. If you can't get on Blackboard, for this course, that indicates they removed you. So take care of it, and then they'll put you back in. If you can't get on Blackboard, you can't hear me say this either, can you? Okay. So, sorry about that. All right. Provided that there exists at least one function phi that satisfies the relation, that's G that we have from up there, as well as the differential equation on I. On that interval I. Now, to me, that's a really mealy-mouthed kind of definition, okay? It doesn't really say anything very clearly to me and say, oh, okay, I see what they're talking about. I don't get any of that. It's pretty fuzzy sounding, okay? I think what we'll do is look at some examples and we'll verify an implicit solution, okay? And that's what example 5 is doing. Here's a relationship. Let's go on and clear the page here. The relation x squared plus y squared is equal to 25. Now, why do they call that a relation and not a function? What is that in equation 4? Look familiar to anybody? What's that? Okay, what's the geometric shape that would? Say again? Yeah, it is a circle of, you can give me a little more than that. Radius 5. That's a circle of radius 5. Is that a function? Fails a vertical line test. It intersects twice. That's why they call that a relation, not necessarily a function. Okay. Now, that relation is an implicit solution of this differential equation. Here's the differential equation. dy dx is equal to minus xy. On the interval -5 to 5. Now, I would have been real tempted to say bracket -5 to 5 because that's all covered by the circle. But, seems like I see some problems there. That would be -5 to 5 should show the values for your independent variable. What is your independent variable in that problem? Help me. What's the independent variable here? Would it help that for you to ask which is the dependent variable here? Huh? Y is the dependent variable, x is the independent variable. But I still see a problem here because, no, I do not, okay, I was looking wrong. Now I see why they put parentheses there. Because if you put a bracket there, that would include x equal -5 and x equal 5. But at those two places, guess what? Your y is 0. And y can't be 0. Because minus x over y. So that's why they put parentheses right. Even though the circle that you said this described, it, those extreme radii of the circle, +5, -5, can't be included in the differential equation because the y is not defined. The y is 0 there, and the you can't have y 0 in the denominator there. Okay, so what it says that on the open interval. So what we do is do implicit differentiation to see if indeed that's true. How do we do implicit differentiation of that original equation? You remember? This was back Cal 1, I believe. We'll take the derivative of the first term with respect to your independent variable, x. What's the derivative of the first term? 2x dy dx. Okay, we just won't write that down. I mean dx dx. Dx dx is 1, so don't worry anything else. Next, plus 2y, but y is a function of x, so you do need to put dy dx, right? Equal to, what's the derivative of 25? 0. Okay? Now, what we need to do is solve that for dy dx. So let's first subtract 2x from both sides. And now these go out, and we have 2y dy dx is equal to negative 2x. Now what to get it to look like above? Isolate the dy dx, which was how would you do that? Divide by second. To isolate the dy dx, get it alone, the naked dy dx there. Divide by 2y. Okay, so divide this by 2y. Okay, the 2y's go out here, the 2's go out here, and what do we have? We have dy dx is equal to minus x over y. Sure enough, that is true on the interval minus 5 to 5. Why on the interval minus 5 to 5? Well, number one, it's not defined outside of that interval at all. You can't have any x 6 or greater, or less than negative 5. You can't, because there's no y that would give you a negative number to balance that out. If x were 6, it'd be 36 plus y squared is equal to 25. That means y squared is equal to negative 9. Can't happen. Not in the real number system. Okay? But it can't even be x equal negative 5. If x were equal to negative 5, then that would be 25 plus y squared is equal to 25. Then y squared would be 0. So y would be 0. But if y were 0, that's not any good, because you can't divide by 0. So that's why we have to only restrict it to minus 5 to 5. That defines the interval in this. Now, there's not really any other way you can verify this is a solution, because you can't solve this for either x or y without having the other variable involved. Okay? So that's why this is an implicit solution. You had to do implicit differentiation to get that result. That means you had to have a dy dx. You took a derivative of this, but had a dy dx and solved for that. You couldn't isolate the y and just go from there. Or really you could, if you had broken this into an upper hemisphere and a lower hemisphere. In other words, if you, rather than writing the circle, whoops, that's not very pretty. This is 5 minus, this is 5 minus 5 and minus 5. This is 0 minus 5. This is 5, 0. This is 0, 5. And this is negative 5, 0. Okay? If you had done the top half of the circle, let me do that in a different color. Y'all have a preference on what color? Second? Blue, okay? Light or dark? Okay, I'll do dark. It might be easier to see. I'll try to do dark if that would be. Okay, that would be open circle here, open circle there, and just this half of the hemisphere. Semicircle, okay? Now, if you did that plus, give me another color. Second? Red, Okay, we'll do the dark red. And then had open circle here and here, and done the second half of the function to be like that. Yeah, you'd had the whole circle. You couldn't include either one of these, but if you did this piece and that piece, then you could have done that. Well, that would be y is equal to plus the square root of 25 minus x squared, and this would be y is equal to minus 25 minus the square root of 25 minus x squared. Yeah, that would have given you two functions, and that would have been fine. They still add up to this, but you have to exclude the minus 5 and 5 because of the division by y there. You can't divide by 0. Okay. Now, a few more terms. This first section is definitions and terminology. Okay? We've just done explicit and implicit solutions. Explicit if you have y is equal to some function of x. Implicit if you have some complicated y's and x's in there that you can't separate out or find it difficult to, then you can do implicit solutions. Okay? Now, the next, we're talking about, families of solutions. Okay? Now, study of differential equations is similar to that of integral calculus. In some texts, the solutions phi is sometimes referred to as the integral of the equation, and we graph is called an integral curve. So, integral of an equation, you're familiar with that term, I hope. So we have, oh yeah, I know, I changed that. Sorry, I forgot. Okay. My eyes are burning. I don't know why. I think part of the reason is I didn't quite have time to finish lunch today. So I ate, but I didn't get to drink much, and I'm somewhat dehydrated. That's why my voice is going on me. So if you had something like dy dx is equal to minus 2x plus 7. That's a legitimate differential equation, right? Well, what might you do? Now, this is something. You could write that as a differential equation. Dy is equal to minus 2x plus 7 dx, and then integrate both sides, and you have y is equal to minus x squared plus 7x, generally plus c. Okay? That would be a differential equation. You take the integral of your differential, if you can do that. It's called separation of variables. So that would be so if you did that, and I did a real simple one, that would be a parabola which opens downward. Okay? And I'm not going to say what parabola, okay? Because you could have a plus c here, which could elevate it or reduce it, so you could have a whole family of parabolae that could fit that solution, okay? And until you know a value, you don't know. So that's why you get a family of curves. Goodness, my eyes are dry. They did a different problem here. They didn't do it, they just talked about it. And it's sort of like what we did on the last slide, how we started that one. So let me erase all this thing. If you had a first order differential equation that read something like that, f of x, y, y prime equals 0. Okay? Some function of x's, y's, and y primes equals 0. First order, they don't say linear, but first order differential equation. The maximum derivative of your y is the first derivative, so that's the first order. Okay. Goodness gracious. Okay. Now, if you were to solve that, you usually obtain a solution containing a single arbitrary constant parameter c. Okay? Because set that up if you can, separate the variables if you can. When you do an integration, it's an indefinite integral, you're going to have a constant. dy dx is going to produce one constant, and that's called a one parameter family of solutions. Okay? And that solution will probably look something like this. G of, you'll have x's in it, you'll probably have y's in it, and you'll have that constant c. And that's going to equal 0. Okay? Now, I'm not sure if you're used to doing it or thinking of it this way. In other words, g prime, or if you take the derivative of g, plug it into what you have up there, you should get your f, that series of solutions. Okay. Now, when solving an nth order differential equation, that would be f of x, y, y prime, y double prime, dot, 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 up to y to the n. And you put it in parentheses to let you know you're talking about the nth derivative of y, not y raised to the nth power. When I said it, I realized it probably could be misconstrued. Okay, if that's your function, and that's equal to 0, then you typically are going to have a solution. G will also depend on x, it'll depend on y, it'll depend on y prime, it'll depend on dot, 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 all the way up to and including y to the n minus 1. It will not have an n term, y, the nth derivative, because that's what you're solving for. So you wind up with all that. Well, and I'm sorry, I forgot to put in a c. Okay? I'm not doing this very nicely. I thought this might, and a constant c equals 0. But then you can imagine that's just something that looks like what you had before, only one less. So if you do the next derivative and the next derivative and the next derivative, every time you do a derivative, you get another constant. Not the same constant, so you wind up with not this, but g, a function of x and y, but then a c1, a c2, and a dot, 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 up to c to the n minus 1. Okay? No, I'm sorry, c to the n. You have n c's. Okay? I was thinking you had one less than what you have, but you do have exactly c. Okay? Because if you think about it, you had n derivatives here, 1, 2, 3, 4, 5, up to n. So that's not counting the y or the x. So when you take each of the derivatives, that's going to give you n c's. Okay? I don't care what you name your subscript. You can have this being the c for that one, and this for that one, that, but you count them down. Or other way to do it, that c for that one and that one, and count them up. Or you could have this is the one for this one and this is the one for that. It doesn't matter how you arrange them. You're going to have n of them. N. So that would be an n parameter family of solutions. That means a single differential equation can possess an infinite number of solutions corresponding to the unlimited number of choices for the parameters. Okay? A solution of a differential equation that is free of arbitrary parameters is called a particular solution. So this is an n parameter family of solution. If you had accounted for every variable, say that you had boundary conditions or you knew enough about it to know that you had to have this one, if you had that circumstance, a solution of a differential equation that is free of arbitrary parameters is called a particular solution. And that would have no C's. Okay? Free of those arbitrary parameters. Let's look at one. Example 6. The one-parameter family, y is equal to cx minus x cosine x. That could be, and they say it is, an implicit solution of this linear first-order equation. xy prime minus y is equal to x squared sine x. Okay? It's saying this is a particular solution for that. No parameters needed. No, I'm sorry. It's not saying that. This is a one-parameter family. Okay? It's an explicit solution. It didn't say it was a particular. Explicit solution. Sorry about that. I was reading wrong. Is an explicit solution of the linear differential equation that. On the interval minus infinity to infinity. That covers everything. Okay? It says verify that. How would you go about verifying it? How would you verify that's the solution to that differential equation? Yes, let's start with the y prime. That's all you need too here, because that's what. So y prime is equal to. Take the derivative of that equation, that solution. C, that means yes in Spanish, okay. Now you got a product rule. What would that give you? Did you say x sine x? X sine x. Okay, not quite. That would make that a plus. Okay, because derivative of cosine is negative sign. But you also have the product rule, which is, remember it originally was a minus, so let me put the minus back in there. Cosine x. Okay, what you did, product rule, you appear to have done the first times the derivative of the second, that made it change the sign, plus the second times the derivative of the first, which is just a minus 1. Okay? So that is your y prime. Now let's see, verify that that solution will satisfy that differential equation. Well, this says x, and your y prime is c plus x sine x minus cosine x minus your y, which is a cx minus x cosine x, and supposedly that's equal to x squared sine x. Doesn't really, yeah, well, it may work. So let's see what we have here. Multiply through clear parentheses. That would be cx plus x squared sine x minus x cosine x. Everybody see what I'm doing? Minus cx plus x cosine x, that minus sign distributed inside, is that equal to x squared sine x? Well, let's see. Here we have a cx, there we have a minus cx, right? Okay, that added to 0. Here we have a minus x cosine x, there we have a plus x cosine x. That adds to 0, and sure enough, x squared sine x is equal to x squared sine x. Yes, that solution, it's a one-parameter system, satisfies that differential equation. And it does it on the entire interval from minus infinity to positive infinity. Okay?
So you plug y prime into that solution.
Say this again now.
Plug y prime into that equation.
Okay? Yeah. We had what x was. They gave us that. We calculated what y prime was. You followed that, right? Okay, now plug back in. X times y prime, which is this thing, right? Minus y, which is that thing. Supposedly, that's equal to this thing. That's what I plugged in. You plugged in the y prime where y prime was, plugged in the y where y was, and then just wrote down the x's wherever they were. Okay. And then when you clear parentheses, the x times c is x, or cx. X times this would be x squared sine x. X times this would be a minus x cosine x. Then when you negate the y, this one, that would be a minus cx plus x cosine x. And supposedly that's equal to the right-hand side. Now we look at these and see the cx and minus cx go out. The minus x cosine x and plus x cosine x go out. And that merely leaves you x squared sine x is equal to x squared sine x. You verified this solution, this equation was that one parameter system was a solution to that differential equation. Ordinary, linear, ordinary differential equation. Okay. Now, figure 113, and only one of you has a book so far, right? Okay. All right. That one parameter system, this, as you put different values for C in there, you can come up with different Y's. Okay? Why not? Okay? And they have graphed them here. That thing right there, Cx minus x cosine x. Notice when x is 0, that whole thing is 0. So everything goes through x equals 0. Y equals 0, 0. Everything goes through that. But then when you go larger x's or smaller x's, the x's terms get bigger. The x cosine x basically stays between plus or minus x, because cosine stays between plus or minus 1, so you're subtracting things from it. So you get a whole family of curves here, depending on what c values you would have. C is equal to 0, x cosine x, that would be the blue curve that you have here, okay? C is equal to something greater than 0, and you'd have a pink curve here. C is less than 0, you have either the yellow curve or the green curve, and you can have all sorts of different values there. And they just, you get a family of curves, depending on the value for C. Okay? Now, if you knew enough about the problem to know that when x is equal to some value, y's got to be some other value, plug that in there. Put in your x's on the right-hand side, the y on your left-hand side, solve for C, and you can figure out which one of these curves you happen to be living on. Okay? But the minus x cosine x would be when C would be equal to 0. And they graph that one there. That's the blue curve in the graph. All right. They then give us a 2-parameter family. This is another problem. The string gets all tangled up around the pen. So let's clear that stuff out. Here's a 2-parameter family. Y is equal to C1 e to the x plus C2 x e to the x. They say that's an explicit solution for this linear second-order differential equation. Y double prime minus 2y prime plus y is equal to 0. Haven't we seen that somewhere before? Flip back to example 3, B, the one we started with today. Y prime, double prime minus 2y prime plus y equals 0, and we had a solution, x e to the x. That was one solution, and I said you could have others. We mentioned several, okay? For instance, 1, 0, that worked too. So, but now we have a 2-parameter system. Now, we go through the same procedure we did before. What do we have to do to show that is a solution? Take the derivative. Y prime is equal to C1 e to the x plus C2 e to the x plus C2 x e to the x. You're absolutely right, okay? Because when you take the derivative of this part, let's just hold out the C2 for a minute. Yes, this times the derivative of that, that's this part, plus derivative of this times that, that's this part, and then multiply C2 by both of those, that's your solution. But we got to do it again, don't we? Y double prime. What would that be? C1 e to the x plus C2 e to the x plus C2 x e to the x plus C2 e to the x again, because derivative of this one is that one. Derivative of this has 2 parts. Product rule, x e to the x, when you do this times derivative of that, plus this times derivative of that, that's another 2e to the x. Well, looky here, you got 2 of those, so we can simplify that a little bit as C1 e to the x plus 2C2 e to the x plus C2 x e to the x. Now let's plug in to our equation the y double prime. That's this thing I just wrote down. That would be C1 e to the x plus 2C2 e to the x plus C2x e to the x. That's the y double prime part. Minus 2 times your y prime was C1 e to the x plus C2 e to the x plus C2 x e to the x plus y. The y was C1 e to the x plus C2 x e to the x. Okay? And supposedly this thing's equal to 0. Don't know for sure, but let's see. Well, what we got to do is go back and clear parentheses. A lot of writing. C1 e to the x plus 2C2 e to the x plus C2x e to the x minus 2C1 e to the x plus 2C2 e to the x. I messed something up there, didn't I? No, I didn't. That's fine. Except it's a minus. That's what I knew. Something seemed wrong there. That's a minus because I was multiplying minus 2 times that. Okay. Minus 2C2x e to the x plus C1 e to the x plus C2x e to the x, and supposedly that's equal to 0. Let's see if it is. Here's a C1 e to the x. There's a minus 2C1 e to the x. That gives you a minus C1 e to the x plus C1 e to the x. Sure enough, the 2 pluses and the minus 2 minus, those add to 0, right? Let's see about the C2 e to the x. There's a plus C2 e to the x, a minus C2 e to the x. Those add to 0. Then you have a C2x e to the x, another C2x e to the x, but then a minus 2 C2x e to the x. Yes, they all add to 0. So you wind up 0 is indeed equal to 0. So that two-parameter solution does work. Okay? Now,
How do you get rid of the C1 e to the x again?
what's that?
I said, how do you get rid of the C1 e to the x?
Say that one more time. C1 or C2?
C1.
They add together to 2C1.
Oh, okay.
You see, did you say C1 or C2?
C1.
C1. Okay, there you had 1 from here.
Uh-huh.
You had a minus 2 C1 from there, and then you had a C1 from here. Well, this C1 and that C1 adds to 2 C1. Here's a minus 2 C1. So that adds to 0. Yeah. And that was, maybe I should do different colors, you know, when I did the crossing out so you can see those. Let me try that. Pick a color, any color. What'd you say, orange? That's orange, okay. Sounds like an Auburn fan, okay. Okay, let's do the C2s in orange. We'll leave the C1s in black as a plus C2 e to the x and a minus C2 e to the x. So those went out. Let's do another color. Pick another color. Say again? Purple, okay. I'll do that purple, okay. The C2x e to the x, a minus C2x e to the x, and another C2x e to the x, the two pluses and 2 minus, that adds to 0, okay? And then the C1 e to the x did the same thing. Okay, I don't know if that's helpful or not.
Yeah.
Okay, good deal. Okay, now, they draw here some of the solutions based on those, depending on what C1 and C2 were. Okay? Figure 1.1.4, this one right here, okay, showing several of the double infinity solutions in the family. The solution curves in red, green, and blue are the graphs of the first one. I take it that's the red one. This red one right here, they got from 5x e to the x. In other words, they said the C1 is 0 and C2 is 5. And when they did that, they gave them that red curve. The second one, y is equal to 3e to the x, that had C1 equal 3, C2 equals 0. And that gave the green one. That's this one that goes just like up like that. And then the third one, the blue one, I think it was, yeah, blue, is 5e to the x. C1 is 5 and C2 is -2. And that gave one that went up like this and then down like that. So you see, you can get all sorts of different things. Was that someone for me? Huh?
I don't guess so.
Okay. Could be someone coming up in the physics class, could it?
3 or 5.
3 or 5. We've got 10 more minutes. They may have just been early for physics. Okay. So, anyway, so you see different choices of your C1s and C2s could produce any of a huge family of curves. You get an infinite number. You can't draw them all in one thing because you can use any values for C1, C2. They showed you 3 of them. They have at least 3 more that are black, 4 more that are black that comes with different combinations of those. Okay, another terminology issue. Sometimes a differential equation possesses a solution that is not a member of a family of solutions of the equation. That is, the solution cannot be obtained by specializing any of the parameters in the solution. Such an extra solution is called a singular solution. It is a solution, but it doesn't depend on any constants. For example, here are a couple, and this seems like something maybe we did earlier, but in case we didn't, let's go and do it now. Erase all this. All right. It says we have seen that y is equal, oh, let's go back to black, okay? Get that. Y is equal to 1/16 x to the 4th and y is equal to 0 are solutions for this differential equation. dy dx is equal to xy to the 1/2. Okay. Now, before we do anything with this, I want you to think about it in a couple of other ways. What kind of differential equation is that? 3 classifications, right? It's a nonlinear because the y is to the 1/2 power. Good pickup. Ordinary because it's dy dx, not a partial of y with respect to x. And first order, because you have the maximum derivative you have in there is the first derivative. Good deal. All right. That was just review. Okay. Now, we are saying that those two are solutions for that differential equation. Okay? Let's verify those quickly. What would you have to do to the first one? Yeah, take a derivative. dy dx for the first one would be what? Take the derivative of that. Second? 1/4, isn't it? 4 times 1/16. It'd be 1 over, what did I just say, 4, x to the 3rd. And let's see if that then, when we plug in here, 1/4 x cubed, is that equal to x times 1/16? Oh, I'm sorry, 1/4. Where did it? Yeah, no, that's right. X times 1/16. Okay. Sorry about this. Hold on just a minute before I do something that's really stupid here. Okay, we need one more step in here. I wasn't paying attention. We found out what y prime was, dy dx. We also have to figure out what y to the 1/2 is. If this is y, what is the square root of y? Yeah, here's your y. Say again? 1/4 x squared. Perfect. Okay? Take the square root of 1 is 1, square root of 16 is 4, so it's 1/4. Square root of x fourth is x squared. Okay, so now let's put that in. 1/4 x squared. And sure enough, look at what you get. Multiply that through and you get 1/4 x cubed, and that's equal to 1/4 x cubed. Yeah, that works. Let's do the other one. Not going to be too hard, is it? Y dy dx is 0. So let's see what we have. we have 0, that's the dy dx, equal to x times, what's the y to the 1/2? Square root of 0. Sure enough, that checks too. So both of those do work. The second one there is called a trivial solution. Y is equal to 0. That works, but it's not a very elegant, meaningful. It doesn't tell you a lot, but it does work. Okay. So both of those are solutions of that differential equation. And they're good for all real numbers. X's, okay? Not Y's, but X's. In section 2.2, in another chapter, we'll demonstrate by actually solving the differential equation of that possesses a one-parameter family of solution, and when C is equal to 0, resulting particular solution is the one we just did. Y is equal to 1/16 x to the 4th. But notice that the trivial solution, y is equal to 0, is a singular solution since it's not a member of the family, and they just say, and they not proving it, not showing anything else, y is equal to 1/4 x squared plus c. That is your one parameter family of solutions. Now, I don't know if you've noticed this yet, but if you have first order, you usually have one constant. Remember the one we did just before this? Second order, we had two constants, C1 and C2. Okay. So, first order, one constant. Now, what they were saying is, set this equal to 0, you get that solution. That solution. No? Did I write it right? I don't think I did. Oh, no, I didn't. This was squared. Sorry about that. Something was wrong. If C is equal to 0, square this and you get 1/16 x to the 4th. That's the solution we got there. But there's no value of C you can put in here that's going to give you that solution. So that would be a singular solution. It doesn't fit in your family. This one fits in the family. C is equal to 0. There is no place that y is equal to 0. Though it is a solution, so that's a singular solution for that set. Okay. Okay. Now, everything we've done so far, when you see something like this, that indicates y is the dependent variable, x is the independent variable. But you know in Cal 3, right, you introduce, in fact, maybe a little in Cal 2, we introduce parametric equations, where x is a function of t and y is a function of t. So they're both dependent on some independent t. So then lots of other things open up. So it's example 7 is going to give us an example of some different symbology we can use and do use. What's that? Is it? How could it be? We're just having so much fun. So we're going to have to start with example 7 next time. Sorry this is moving so slowly. Okay, but we're almost through with this 1.1. We'll get there one of these days. Okay, next time. Okay. So let's do any of the odds 1 through 7. Do number 9, either 11 or 13 or both. Either 15 or 17 or both. Do number 19. Try to do either 21 or 23. 25. Maybe we'll stop there. And let's stop before that. Stop at 23. Because 25, we haven't done that yet. So stop at 23. Okay. That's a few more than I gave you last time, wasn't it? I hope so. Okay. We'll see. And we'll pick up. We'll finish 1.1 next time and move on to 1.2. Okay? Good deal.